might start right now.
Good afternoon, Doctor. My name is Kirubanishri Dodofratnam, and my metric number is CD210274. Today, I would like to present about our experiment title is Buckling of Truth, presented by Group 4B. Now, I would like to start with the theory. Euler's theory predicts the axial compressive force required to initiate buckling in a long thin strut. Ideally, a perfect straight strut, when subjected a purely compressive load, will compress and not buckle. Buckling is therefore a result imperfection that prevent the load from being applied perfectly axially. Example from eccentric loading and lack of initial straightness, the combined effect of the imperfections and overall buckling behavior is predictable when long struts are operate under elastic conditions. We need only derive an instability criterion from the lateral deflection of occurs. Next is the result for the experiment 1, which is pin out. This is the result. And for table 2 is pin fixed, and the last is for table 3 fixed. And next my friend will explain.
Alright, for observation, in the first part, the strut was set to have a pin end, and first we use the shorter strut, and then we apply the force by turning the handwheel, and after we turn the handwheel, we can observe that the strut slowly bend. At a certain point, the value suddenly decrease. As the length of strut increased, the max value obtained decreased, and it became easier to turn the loading handwheel. In the second part, we set the strut to be pin end and fixed end, and the strut length decreased by 20 millimeter as in the clamping process. And as the length of the strut increased, the max value obtained decreased, same as before. And the third part, we set up the strut to be fixed end, and the strut length was reduced by an additional 20 millimeter. Same process as the length of the strut increased, the max value obtained decreased. If we compare the difficulties in turning the handwheel, the strut with fixed end setup was found to be the hardest to turn, while pin end to be the easiest. That's all. Next calculation.
Okay, so for the calculation part, step one, we need to find the second moment of area, which is in the meter square. I, we are using the formula below. I equals to BD cube divided by 12. And then we use the Young modulus, which from the reference, we get E equals to 69 gigapascal. And the length of the strut we obtain from the experiment. The step two, we need to substitute the I, E, and L that we found in the step one, and we substitute into the Euler load equation. Then we can obtain the theoretical buckling load. Below here, I have shown the formula for the Euler load equation, which is pi square EI divided by L square. And we have three type of strut, so we have three formula for the Euler load equation. Okay, so step three, we need to find the L. We need to find the 1 over L square, which is this is related to the gradient of the graph. Yeah, so I will leave for the discussion.
For discussion, the first one is the graph of buckling versus the 1 over L over power of 2. So the graph is, for the first one is the pin. So for the experimental, the graph is increases, but for the theoretical, it is increased linearly. The next one is fixed graph. As we can see, the graph for experiment increase, then it decrease, and lastly it increase back. But for the theoretical, it is increased linearly. The last one is the pin fits graph. But for the pin fits graph, the experimental one, it is increased. Then for the theoretical, it is increased but then decrease and increase back. The second one is the gradient of history and experimental. For the experimental gradient, we get 10.19. For the theoretical gradient, we get 9.11. So the experimental ratio is 1. The theoretical gradient is 1 also. So the pin fits, we get the experimental gradient is 7.17, while the theoretical gradient we get at 10.29. So the experimental ratio is 0.7, then the theoretical gradient is 2.01. For the fits experimental gradient, we get 24.48, while the theoretical gradient, we get 36.05. So the experimental ratio is 2.4, and the theoretical gradient is 3.96. The third question is the ratio between strut length and collapse load. So according for calculation, the Berkeley load will decrease when the strut length is raised because the two variables are inversely related. So from the experiment, as the strut length is increased, so the Berkeley stress will decrease. The last one is the importance of understanding the collapse load of framework for instance in a building structure. So the important is, for example, the collapse load for building structure are crucial because they are affect the lift of people who occupy the structure. The second one, we can also lessen or completely avoid financial damage brought on by structural collapse, which necessity maintenance and renovation work by determining the collapse load of the framework. The last one is to track the inelastic earthquake performance of frame structure in earthquake prone areas. It is crucial to understand the collapse load.
Hello, doctor. Good evening.
Yeah.
My name is Mason, son of Khalis Paran, and my matrix number is CD210325. So now I would like to present about the conclusion and reference. So for the conclusion, we look into slender column buckling and the link between length and fixing circumstances and buckling load. With varied end fixing conditions, we also understood the nature of deflection and deflected slopes. The length of the strut and the end fixing, which can be E-pin end, pin fix, or fix end, have an impact on the buckling load. We were able to gain a better understanding of the experiment as a result of this experiment, and the objective was achieved. One of the problems faced during this experiment was inconsistent results compared to theoretical values. To overcome this problem, we should ensure that the experiment apparatus is maintained well. We can also repeat the experiment several times and take average readings for more accurate and consistent results. And this is the reference. So we use this
Mm.
reference for more understanding for this experiment. So
O-
that's all from us.
Okay.
Thank you so much.
Okay. Thank you. I only have three questions. First, can you show me your graph? Okay. Okay. Pin. Okay. Pin N, and then pin fix. Next.
Sorry, doctor, can you repeat the
Next.
question?
Next.
Next.
Okay.
Okay.
Okay. This one is fix N. Pin fix. Okay, this one pin fix. Okay, so based on these three graph, can you conclude anything based on these three? What happened during your experiment?
When the buckling load increase, is the x-axis 1
One
over
over L.
L2. That one is
Why
Uh,
those two? The theoretical is linear, but this one is sometime up, sometime down.
oh, this one probably caused by the data when we obtain right from the observation. When we compare the turning well, right, maybe there is some error inside when we turn the hand well. So probably the strap sometimes will be tightened or sometimes will be loosened bit. So there will be some error inside the data obtained. Yeah. Because since 1 over L square, right, the inverse of L square, we actually obtain from the theoretical. And the buckling load, we actually obtain from the data. So
Mm.
there will be some, how we say, there will be some
Mm.
experimental
It's
error
a
inside
error.
the number 3 graph, yeah, the pin fix graph.
And then according to your observation that you mentioned that the higher the length, then the higher the numbers of the deflection. Okay, my question is how to identify the maximum length of the buckle, the buckling strut. Let,
How
you
to
just
obtain the maximum length, right?
let's say you are in construction base, and
Mm-hmm.
then we already know about this buckling strut principle, which is the higher the length, the
Mm-hmm.
higher the deflection. Okay, so
Yeah.
how we are going to limit, or maybe as a precaution we set the limit, what is the maximum length of this column, something like that.
Oh, okay. So actually, we need to from the equation, right? Actually, we need to determine the Euler load equation and the I as well. Because the I, we have the BD, which is the width and also the not diameter, the width and also the
Thickness,
how I B
height,
is
thickness and height of
thickness
the cross
thickness.
section.
Yeah, cross section area. So actually, this will affect the second moment of area we obtain.
Mm.
Depends on the B and D. As we getting B and D larger, then the Euler load will be higher. Yeah, and if the L if the L obtain we obtain is larger, then the Euler will if the E and I will be constant, then the Euler load will increase. So actually, we need to set a maximum maximum length for the strut after 20. How
Yeah,
many
yeah,
is
yeah.
it?
Another point is you have to mention also about the material selection of the column,
Oh, material
and
selection.
another, uh, and then the final question is about, let's say this topic is become to your final year project. So what is the variable that you want to take note, ataupun you want to identify in your concern about the parameter, the variable parameter of your project. Okay, okay
Okay,
in
so
this, okay, in this experiment, actually we play around about the length, and also the type of pin end, pin fix, and fix end. Okay, what else, what is the others variable?
cross sectional area of the strut and also the
Material.
material. Just now you mentioned, right?
Mm-hmm.
Material. Just now you
Okay,
mentioned material.
Selection.
Material
why,
selection.
okay, what else?
Because material will be affect the Young modulus.
Mm-hmm.
And second, no, second, the 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 dimension of the strut as well, length,
Mm-hmm.
width, and also the thickness. Yeah.
Okay, good, good. Okay, why I'm asking you about this is because if you, I don't know if you already PSM1 or not. But in PSM1 we have a methodology, chapter 3, And then we have chapter 4 about the result and discussion. In this chapter, actually, we try to identify what we are going to uh, play around about the parameter setup, about the variable that we want to play around. Let's say the times over the temperature, or the apa, the deflection over the length, something like that. The variable.
Oh,
So
okay.
thank you
So,
very much.
okay, sure.
Okay, thank you
Okay,
very
thank
much.
you.
And any
Sure.
question?
Any question?
Any question or any apa ni nak cakap anything lah you want to add up during our class, maybe your opinion, your anything. Okay.
I
Because
have
after this
no,
we you have no idea.
I have no idea. At least we can get a good mark.
Uh, okay. For my concern about the lab is, the lab actually just 1 hour credit. Okay, but please use this experience for your next future lah, about your ESM for final year project, and about, let's say after this you are getting as apa, you are appointed as a structure engineer, as a mechanical engineer, something like that lah. And then use this type of macam procedure, type of macam design of experiment, something like this, as apa, experience during doing this, conducting the lab, for your real career future lah. Okay. Okay, thank you very much. Okay.
Thank you, Doc,
Good
for
to
your,
meet each
thank you,
other.
Doctor, for your advice. Thank you.
Okay. Okay, thanks.
Okay, see you.